Hi guys, this is probability distributions for continuous random variables, part 4. So we're going to wrap it up with this fourth video. This is going to be all of 7.3 from our textbook. Let's just review a little bit. In part 1 of this video, I set the groundwork. In part 2, we talked about the normal distribution and used the empirical rule to analyze it. In part 3, we talked about uniform probability distributions. And here in part 4, we're going to do something that I categorize as other. Okay, so what is other? Let's take a look at what we're doing. The reason why we're making these particular choices is because we are avoiding calculus. We don't want to use any calculus in this. And if you have a probability distribution that has a curvy shape like this, we say it's nonlinear, we'd have to use calculus to be able to find out relative proportions between this and that point within it. Anytime a function has an area underneath it of 1 and follows a few other rules, like for example, it never dips below the x-axis and so on, we can deem it a probability distribution. But if it's curvy and we don't have some workarounds, like we do with the normal distribution with the empirical rule and so on, then if it's curvy and without those workarounds, we have to use calculus. So we're not going to do that. We were able to use the uniform probability distribution because it has a flat top. It's a linear function where the function has a slope of 0. And because of that flat top linearity, we're able to work on it using just algebra techniques and a little logic and thinking. Well, these probability distributions that I call other are kind of similar, but yet kind of different. Let me show you what I mean. Let's imagine that we have a probability distribution that looks like this. Yes, it's possible. This is triangular. I'm going to write out the rule that defines this probability distribution this way. This is a very common way for this thing to be written out. I'm going to say that our probability distribution takes on the function 1/2 x for all values between 0 and 2. You may be wondering why I decided on 2. I'm going to show you that in a minute. And the value of this function is 0 otherwise. That means beyond 2 on the right and on the left. Well, first off, how did I know that it was going from 0 to 2? Well, I decided on 0 just arbitrarily to make it simple, so it was kind of familiar. But I knew that with a slope of 1/2, the right-hand point has to be 2. Why? Because, remember, probability distributions have to be shapes with an area of 1. That's a rule. It can't not be the case. So my right point has to be 2 if my left point is 0, because that's the way for me to get an area of 1. The area of a triangle is 1/2 base times height. So if I take 1/2 times the base length, right endpoint minus left endpoint, might seem redundant to write 2 minus 0, but let's just be careful and go through all the steps. Right endpoint minus left endpoint, 1/2 base times height, we're going to get 1. Let's just make sure that we see what the height is right there. I'm going to take the 2 and plug it into the function to get the height right there. So let me do that over here. I'll erase it very quickly. 1/2 times 2 equals 1. So the height there is going to be 1. So if I multiply that all out, I have 1/2 times 2 times 1, which equals, yes, 1. So it's a good probability distribution. We're on solid ground there. Let me erase this. We're going to do some problems, because so far it's not that hard to see, but working some of these problems can get a little touchy. So let's do a few examples. Let's try this. What is the probability that randomly selected individual or event from this distribution would have a value greater than 1? So what that means is we're looking for, let's say that's 1. I know my proportions might be a little bit off. That means that we're looking for this area. Now there's a number of ways you can do it, and you can make it complicated if you want to. I think the easiest way to do it is for us to find the area of this dotted unwanted zone. Since we know the area of the whole distribution is 1, we can find the area of the unwanted zone to the left and subtract it from 1, and what we'll be left with is what we do want on the right. So let's go ahead and do that. I'm going to find the area of this unwanted triangle. So it's going to be 1 minus the unwanted portion. The unwanted portion is 1/2 times, because it's a triangle, base 1 minus 0, that's the base length, times height. So we're going to have to figure out the height here. You may already see it and be doing it in your heads, but let's be careful. I'm going to do it formally over here. F of x equals 1/2 x for values between 0 and 2, and 1 is most certainly between 0 and 2. So I'm going to plug the 1 into the function, and I have 1/2 times 1 equals 1/2. So that tells me that the height of this function at this point is 1/2. So 1/2 base times height. And I'm running out of space on the bottom here, but I have 1/2 times 1 times 1/2, which is the same as 1/2 squared, 1/2 times 1/2, which is 1/4. So area of 1 minus the unwanted zone is 1, I'll finish the problem right here, minus 1/4, leaving us with 3/4, and that's the answer. Let's do another one. I'm going to set this up, I'm going to pause, I'm going to let you work it, and then I'll come back and I'll give you the answer. Here's the next one. It's a little bit harder, but I think you can do it. Let's get the probability of randomly selecting a score that would be between 1/2 and 3/2. Now we're going to need a new triangle for this one. Let's draw a picture of what we want first. What this question asks us is, what is the area between 1/2 and 3/2, which is 1/2? We want this. How are you going to do that? You can use a modification of the techniques that we just used on the last problem. Why don't you go ahead and pause, work the problem, and come back. Don't give up. Okay, let's do that. Basically, I hope some of you guys saw or suspected that we really just are going to do more or less the same technique, only this time we need to figure out the area of a different larger zone. I'm still going to define an area that I do not want here. But first, I'm going to find out the area of the larger zone that I'm going to subtract that from. It's no longer a case of me being able to subtract from the whole distribution, because I just want between these 2 points, 1/2 and 3/2. So I'm going to have to find out the area of the triangle going from 0 to 3/2 first, And then from that, I'm going to subtract the area going from 0 to 1/2. So let's do that. Basically, we're going to be doing the same procedure twice. I'm going to plug in the various numbers into the area of a triangle formula. It's going to be, now this is for the bigger triangle, 1/2 times base. We're doing the whole larger triangle, so 3/2 minus 0, times height. Let me figure out the height at this point. To figure out the height at that point, I'm going to have to plug in this value into the function. So that's going to be 3/2 plugged into the function where x goes. So I have 1/2 times 3/2. And I get 3/4. That's the height. 1/2 base times height. At this point, it's just algebra. That will be the same as 1/2 times 3/2 times 3/4. If you multiply it all the way through, you're going to get 9/16. So that's the larger triangle. Let's figure out the area of the smaller triangle that's unwanted, and we'll subtract. I'm going to leave just that value there. Okay, smaller triangle. 1/2 times base times height. Again, we're going to plug in our x value into the function. So the function is 1/2 x, and I'm plugging in 1/2 for our x, and we get 1/4. So that's the height, because I plugged it into the function. 1/2 times 1/2 minus 0 times 1/4. And that's going to come to 1/2 times 1/2 times 1/4, or 1/16. Great. The larger triangle has an area of 9/16. The smaller unwanted triangle has an area of 1/16. So if I subtract the unwanted area from my larger area, I'm left with just what I want. You do not have to reduce that to 1/2 if you don't want to. For our class, for probability and statistics classes, it's generally acceptable not to reduce. The answer is 8/16. Okay.